Okay, so good morning and welcome to this morning session, which is probably a dinner session for our speaker in Nagoya. So today we start with Masaki Shigemori, who will tell us, I guess, about his recent paper on interpolating between multicenter solutions. So Masaki, you have 1 hour and I'll give you a 10 minutes warning if you want, okay?
Okay, thank you very much. Thank you very much for the introduction, also for the opportunity to present my recent work. Okay, is it changing? I can't see my own slide. Okay.
Yes, this
Yes,
changes.
yes.
Okay, so in some sense, this talk is a continuation of my talks in the previous meetings, which is okay, and this is kind of small progress towards solving a homework problem that I assigned myself. And of course, I don't mean that you have to have attended the previous meetings and heard my talks to understand what I'm going to talk about. And hopefully this is going to be a very easy listening talk before the heat that we expect in this afternoon or late at night. And this is not going to be directly related to the page curve or islands at all. Okay, but it's about black hole microstates. So it's going to be about the D1, D5 system, which is the setup where you have ADS 3x3 dual to the D1, D5 CFT that most of us are familiar with. And that's where D1, D5P, the 3-charge black hole lives, or the Strominger-Vafa black hole lives. And in this system, we have the so-called Lumimotor geometries, which are the 2-charge microstates. And also we have multicenter solutions. So there are different families of microstate geometries. The first one is a Lumimotor geometry. That's the half BPS geometry. And also there are multicenter solutions. That's been known for some time, but we don't really know the general CFT understanding. And also there are superstrata that we have been hearing in this conference, and they are the most general microstate geometries that we know so far. Okay. So let me start with an introduction and summary. In short, the question is, what is the bulk dual of the interpolation between the CFT states? This and this, although I have not explained what these are. Okay, I will refer to David's nice talk yesterday for some details of the CFT. But okay, so this is the D1, D5 CFT, which is the old fold CFT. And if you want the state in the CFT, they are supposed to combine many so-called strands of different length so that the total length is capital N. And here what we have is some kind of strand plus length 1 to the n. So you have length 1 strand n times so that the total length is n. And you have plus that you don't have to worry about at this point. These are some R charges. And this is known to dual to some 2-center solution. So you have some 2 centers like this. And you want to interpolate between this state and some other state, which is plus 1 gamma n. And this is basically the same strand of length 1, but it's been spectrally flowed. So its spectral flow is some kind of transformation, which in some sense excites this strand by some amount parameterized by this n, the spectral flow parameter. And this is known to be dual to some other 2-center solution. Oh, and I forgot to say, but this solution and this solution are both smooth in string theory sense, and they are microstate geometries. And this latter one was studied by, okay, this is an example of the GLMT solutions. Justo, Lunin, Mathur, and Turton. So the goal is to interpolate between these. And note that, one note is that we won't really be able to answer this question in this talk, unfortunately. And this interpolation, it's easy. It's good to look at this diagram in which you plot the states of the theory. So you have, this L0 is basically the energy, and this JL3 is the arc. It's one of the R charges or the angular momentum in the bulk. And so in this plane, there are many states, and the states can exist only above this polygon, which is like a parabola. And the ++1 thing that I talked about on the left in the previous slide is some state here. And the other state is somewhere here when the spectral flow parameter is -3. And I want to interpolate between these states. And by interpolation, on this diagram, on this plane, on each point, in some sense, there are some states. And I'm not talking about taking this state here and taking this state here and taking this state here. That's not what I really mean. I want to take the state here and take the state here and interpolate in this sense, roughly. So when L is 0, then you only have this unflowed strands, and you're here. But if you increase L, you start to have this flowed strands more and more, then you're going to go to this point. So that's what I mean by the interpolation. And why do you want to ask this question? There are many ways to motivate this. This is a key to understanding three-charge black hole microstates, because this is a simple example of fractional or higher modes in CFT. So in CFT, you have many possible ways to excite your strands. And in superstrata that I mentioned, you only excite very basic kinds of modes, L-1 and J-J0, and also some supersymmetry generators. But there are more generators in the CFT, in particular, something called the fractional and higher modes. And if you start to excite them, you're expected to get more typical black hole microstates. And this flowed strand is one of such higher modes, fractional or higher modes. So these are important. And there are many more things that I could say about the importance of this question, like, lifting and BPS, non-BPS, and models in a more Schrödinger, and so on and so forth. But I don't really say it here because it's going to be too long. And if you're interested, you can see my slides from the last October meeting. But I do say something on this slide. So in more general, more generally, you can consider state interpolation of this form. So this part is unchanged, but you start to turn on some flowed strands. So you have N here, but you also have length K. So you have some length K strands, and you excite them by spectrally flowing them, and you have L copies of them, and you increase L. You could have this, and you can get some kind of, we can come up with some hints for the bulk duo of this. And first of all, this state doesn't have to be describable within supergravity, because we are starting to excite all possible things. That means that you're probably exciting some stringy things that you cannot describe within supergravity. And relatedly, this becomes non-BPS away from the orbifold point. It's supersymmetric at the orbifold point, but it's not if you turn on twist operators. And that was observed by Gavan Narain, and it's been studied by Mathur Samir and students and students and postdocs now. And one other thing I can say is that if you take large K, so if this strand is long, then this flow strand is an oscillating string that is going along the equator of S3. That's the ADS3 version of BMN, Bernstein, Multicenter, Stase, and that's been studied by these people. So that's one piece of information. And also, if you consider large n, so if you raise this state to large power, then because you're exciting many copies of the same fin, that you are going to have many fundamental strings on top of each other, and that's expected to puff up into some D brane in general. Okay, so these are some hints of what you expect for this general case. However, I'm being more modest in this talk, and our goal is pretty simple. So to gain insight, we focus on n equals -1. So this is the first state, and you go to this state, okay, with this -1 as the spectral flow parameter, and this is actually equal to ++. And you can more generally consider ++k going to -+k prime. And the goal is to very explicitly see how this these two-center solutions deform into each other. So in the same diagram, we are simply at the bottom of this diagram, and we are going from this point to this point. That's pretty simple. So it's a two-center solution to another two-center solution. So that's the modest goal. And this is merely interpolation between two Lumimotor geometries with different profiles. So in that sense, this is trivial. Yes. And no new solutions in this talk. The purpose here is to see them from a new viewpoint. And we observe some interesting phenomena. And we also develop some techniques useful for constructing more general solutions. So, it's kind of trivial, but there are some interesting things coming out. So that's the point of this talk. Any questions so far? You're free to interrupt at any point. Okay, so what you see is, okay, here is the preview of what you see. So as you go from this one to this one, what you see is this. So you start from this two-center solution. So you have two centers, and then, okay, these are co-dimensional three centers. So this is a point in R3, and as you turn on some bit of minus plus guy, what you see is that this point puffs up into a curve, circle, or latitude line on some spheroid. And not just that. Okay, so you have some D4 brane charge here, and this D4 brane actually splits into two pieces. So some D4 brane is sitting here, so it's localized. So it's on this blue curve, but the rest of D4 brane charge is distributed over this disk, which I can call delocalized charge. And this is because the harmonic functions in this solution becomes monodromic. So there is going to be a branch cut, and on the branch cut you want to associate some charge. And as you proceed with the interpolation, and this disk goes up, and at the point when this other center, so you have some other center here, when this other center crosses the disk, some charge gets transferred from this disk. So this delocalized charge gets some part of this delocalized charge gets transferred to this green guy. And finally, if you move this thing all the way to the North Pole, then you end up with this state. And you are now having a different charge from the charge you started from. So you started with k maybe, but you now have minus k prime or something.
Masaki, a stupid question.
Yeah.
What this is the 4D perspective, but if you look in 5 dimensions, this is just going to be some spiral playing some funny game in 5 dimensions. I mean, this is just
Exactly.
the 4D reduction. Okay,
Yes.
you're going to talk about that, I guess.
Yes. Yes.
Okay, good.
And in 5D, there's yeah.
Go ahead. I just want to understand, why is this charge delocalized? I mean, why can't you just do it with the harmonic function that's sourced entirely on the blue curve?
It's probably good to wait for, I don't know, 15 slides. It's much easier to explain there. So it's the harmonic function is going to be monodromic. And because of that, okay, so, normally the charge is simply the coefficient of the 1 over r pole in the harmonic function. But when you have a branch cut, you cannot define that kind of thing. So in a well-defined, in an unambiguous way. So you have to, so if you want to measure the charge, you start from some Gaussian surface and you want to deform this, but because of the branch cut, you can only deform it to be like this and this. And from this big one, you pick up some contribution from a delocalized source, and also there's going to be localized source.
Okay, but my confusion is the following.
Yeah.
There's obviously a need to deposit some charge or change the charge on the green dot.
Yes.
And it looks like you've made a choice to delocalize D4 brane charge, whereas you could have made a choice not to delocalize it and put it on the purely blue ring. And yet that delocalized charge is going to be obviously instrumental to the charge transfer to the green dot. So it looks like you're making a choice, but then there's an essential physical outcome from that choice. So I'm having trouble reconciling.
Okay, it is a choice. Okay, you have the choice of choosing where to put the branch cut. So depending on where you put the branch cut, you have the choice of saying that, okay, you have this green dot has crossed the branch cut or not. But in the end, finally, when you reach the other point, then there's no choice. This green point has crossed the cut.
Okay, I guess I'm still puzzled why there's a branch cut in the first place and not point charges.
Yeah. I please be patient, and I will try to answer that later.
Sorry, Masaki, I would like to interrupt you one more second since you're.
Yeah, please.
Just a stupid clarification. What is your duality frame? What are your global charges? Since you're saying D4 brane.
Yes, this is the 2A brane, 2A frame.
2A frame. So your global charges are what?
D2, D2.
D2, okay.
Yeah.
And can you describe the same solution in terms of Lumimotor profile for the
elements? Sure.
Are you going to do this later? Or?
Yeah.
Okay.
In 5D, it's trivial.
Okay, good.
In Lumimotor, it's trivial. And this, okay, the last thing is that this is the same mechanism with Gregory Harvey Moore, where they said the following. So if you have a Kautz-Klein monopole, then you have some non-trivial S1, but this S1 actually shrinks at the center. So if you wrap a fundamental string, then we think that the fundamental string charge is conserved, but you can bring it to the center and then it's unwound. So is this fundamental string charge conserved or not? It is conserved because this center, this top knot center can carry fundamental string charge by some B field. So you have some non-trivial 2-cycle at the center of the top knot, and because you can have some kind of Wilson line for the B field. And as you move your fundamental string and unwind that, you are somehow transferring the fundamental string charge to the B field. And this is exactly what's happening. So as you move this disk from the South Pole to the North Pole, you are unwinding in some sense the D4, and you're transferring the charge to the middle center. Okay, so this is the preview of what I'm going to talk about. Okay, you can ask questions at this point. Okay, maybe I will proceed to the detail. Okay, so Lumimotor geometries. So Lumimotor geometries are solutions of 60 supergravity, and this is a two-charge microstates. So they describe all the microstates that you see from the CFT in the bulk. And they are parameterized by so-called profile functions, GI lambda. So this is a curve. This is describing a curve in R4. And this curve is describing the supertube transition of this D1 and D5. So you're binding D1 and D5, and they are going to undergo supertube transition and puff out into some calcium monopole, which is along some curve lambda. And you also have some momentum charge along it. But anyway, so that's what this Lumimotor geometries are. And here is the metric, but well, it doesn't matter. And so what we are doing when we interpolate these two states is the following. So if you have this plus guy, so of length k, this means that I have split R4 into two R2s, and this is saying that in the first plane you are going around a curve along a circle with radius a k times, but in the second R2 you are at the center. And okay, and on the other hand, when you have minus plus k prime, then you're at the center on the first R2, and in the second R2 you are going around a circle of radius b with k prime times. And if you want to interpolate, what you do is pretty simple. You just combine the two. And this, so as you increase lambda, you're going around a circle, along a circle here and another circle here. So this is like a helix in some sense. It's not like exactly like this because you are moving in two different planes, but well, it's like a helix. And computing the Lumimotor geometry, so you want to compute the functions in here by plugging in this profile function. And that can be done in principle, but it's a bit difficult. And in particular, getting the B field of the Lumimotor geometry, so this B guy is a bit of pain. So I did not take that route. And that's not the route that we take. Okay, so that's the Lumimotor geometry in 6D, but there are multi-center solutions in 4D and 5D, and we can reduce Lumimotor geometries to multi-center solutions. So these multi-center solutions are 4D solutions of 4D or 5D supergravity, and they describe in general bound states of D branes. If you are into a frame, you have D6, D4, D2, D0, and this is described in terms of harmonic functions in R3, so which is normally called B, K, L, M, and they are all harmonic in this sense. And in general, the solution can be written like this. So H has a constant term, and you also have many 1 over R poles, where this Rn is y minus an. So y is the coordinates for R3. Then you have some points like this, where this H diverges. It has a pole. And this can be used to construct microstate geometries, and that's what we have been doing for decades. And in here, we are mapping the D-brane charges of the Lumimotor geometries like this. So D1, D5 becomes D2, and calcium monopole is D4. Sorry for this. Maybe this is actually easier. This is to avoid confusion. Now, okay, so we have the Lumimotor geometries profile, and we want to reduce that to the multi-center solutions by reducing the R4 profile onto R3. So first, we have this plus guy, and this, as I said, is a circle in one plane, and it's a dot in the other plane. And we can reduce this to R3 by the standard Hopf vibration. So it's the parameters are like this. And so you have some circle direction psi, and this psi involves this direction as well. So if you reduce this R4 profile down to R3, then it's going to be, okay, this circle is going to be simply a point here. And there's another point that is nothing but the center of this R4. And in this case, we can represent this by a harmonic function for D6. That's 1 over R, B equals 1 over R. And also you have a harmonic function for D4, which is K3. And we have 1 over R minus, where this R minus is equal to Y minus A tilde. So this vanishes at this pink point, and you also have 1 over R. So this is what you have. So you may think that we have only put D4 only here, K at this point, but actually we have to put this minus K charges, minus K units of D4 brane also to correspond to the Lumimotor geometry. Okay, this is a technical point. And okay, so that's one thing. And if you want to consider the other end, then this corresponds to having the circle on the second plane, and this reduces to this pink point here, and the center of the space goes to this center again, and you have the harmonic function B equals 1 over R, and K3 is now K prime times 1 over R minus R plus 1 over R plus, where this R plus is Y minus B tilde. Okay, so this is a standard story, I think. Okay, so that's fine. And that was about codimension 3 centers, but we can talk about codimension 2 centers as well. So these harmonic functions can also have codimension 2 source. Why not? And you may wonder, okay, why do you do it? But there is a reason, because super 2 transition produces such codimension 2 branes. If you have D2 branes, like we do, then they can puff out into some NS5 brane, which is along some curve lambda. So in R3, you can have some curve like this or this. And these curves are not just the codimension 3 source smeared, because harmonic functions are going to be monodromic. So as you go around such a curve, K3 is going to K3 plus some number, the NS5 brane number times V. So it's not a constant shift. It's a bit strange, but it's what it is. Because if you look at the B field, it has this form. And if you have an NS5, B field must undergo a additive constant shift. That means that this part must undergo a constant shift. And that gives you this monotony. So that's what you expect. Okay, this part doesn't play.
These sources are intrinsically logarithmic, right? So that's the origin of this kind of monotony.
Yes, this is logarithmic, indeed. Okay, so now let's look at the interpolating solution. So this is what we have now. And this corresponds to a circle in one plane and another circle in the other plane. And if we reduce this using the hot vibration, this becomes a circle in R3. When we do this, we have to smear because, well, we have smeared the thing. Or we have just project this curve down to R3 so that we don't see the structure in the fiber. But anyhow, it's just a circle. And okay, so what is the harmonic function? So we want to construct the harmonic functions that describe this situation. And the first thing is easy. So D2 brane charges or the D1, D5 brane charges, they must be uniformly distributed over the ring. So you have to have a constant distribution of D1 and D5 charges. So it can be written like this, where this H is, okay, L1, H2 are harmonic functions that correspond to these D2 brane charges. And this H is a harmonic function with codimension 3 source uniformly distributed along the ring. So that if you introduce such a thing, you can do it. And okay, so there is some mathematical description for that. That's easy to construct. So because you have just this curve here, you just introduce a 3D profile. So your F1 plus IF2 is now going along this thing. F3 is just C. And then you consider just this smeared harmonic function. Then what you get is the correct one. Okay, now, so that was easy, but now we want to also consider NS5 brane charge represented in terms of some harmonic function. And NS5 brane charge can be read off from the profile function, because we know how many times we are going around the circle. We know how many times we have to go, how many NS5 branes must be going along this circle. And from that data, you can see that this K3 must have the monodromy. K3 should go to K3 minus K plus K prime V. And this monodromy can be certainly realized if you take K3 to be this, so minus K plus K prime times gamma V, where this gamma is a harmonic function with monodromy gamma going to gamma plus 1. So it's a simple harmonic function. Of course, if you do this, this expression is not going to be harmonic. So you have to correct that thing by, well, adding something. That something can be worked out. So this gamma is a building block. And this gamma can be also easily, well, relatively easily found. So if you introduce one form, 3D one form alpha, which is like this. So this is like the vector A in the Lumimotor geometry. And you define the dual gamma. Then this gamma is the thing you want. So this is like, okay, so you imagine a current flowing along this circle, and then this alpha is the vector potential. And this gamma is like the magnetic potential. But anyway, you can work that out. Okay, now you have found the harmonic functions L1, L2, and K3. Then the other harmonic functions can be fixed by the integrability condition, by which I mean this standard formula. Oops. So you can solve this to find the, yeah.
Just a mathematical thing about the procedure. So at some point you've got a hypergeometric equation, presumably, and that hypergeometric equation has some kind of indicial equation where the indices differ by integers. And so therefore one solution is going to be some harmonic function that's perfectly normal, and then the other solution is going to involve at some subleading order that same harmonic function times a log. Is that the kind of thing that's going on here?
Okay, I don't know which problem you are thinking about.
You said I take this function V, which is harmonic. I introduce something with gamma, which is a log, which has monodromy. I multiply V times gamma as a log. That's the standard structure of the other solution to a hypergeometric equation. And this correction is usually just some other hypergeometric series.
Okay, I don't know that general story. This can be somehow worked out.
But at the end of the day, what you're solving is some kind of hypergeometric differential equation where there are log branches, correct?
I don't know. This is a 3D problem.
Yeah, but you're getting it down to functions of a radius because everything's axisymmetric.
Yeah. Okay. Probably that's right.
Yeah. Okay.
Yeah, but this can be solved even for general profile. It doesn't have to be a Stockholm.
Okay.
Anyway, so
it's a function of two variables, right? You have the radius and you have the z direction.
Right.
Yeah, but but that's But if you can somehow combine them and make it into a holomorphic differential equation, then it's
yeah.
And you do have some hypergeometric function as in the solution, but you also have some elliptic integrals.
Oh my god! Wow. Okay. Got it. No. Okay. It's more difficult than I thought. Yes. Okay.
Yeah. It's not so trivial. And then you can also impose the no closed time light curve condition, which says that this should hold. And so as far as this 4D/5D multi-sensor solution is concerned, you don't care as long as Q1 is satisfying this. But if you want some solution that comes from the Lumimotor geometry, then you have to saturate this solution. Then if you impose that condition, then you're going to get a solution that corresponds to the helical profile. Okay, so here is the final result. So you have V, that's 1 over R, and Z is L1 is that this is this H thing. Z2 is also this H. F3 is 1. K1, K2 are trivial, and K3 has this complicated form. So you have this piece that I just added by hand, and you have to add some extra pieces to make this harmonic. And M is determined by the integrability condition. So, and this can be written in terms of elliptic integral. So this I10, I01, I didn't really show you the definition, but they can be written in terms of elliptic integrals. So this way we succeeded in constructing harmonic functions from 4D, 5D multicenter solution using the input from the profile. This way I didn't have to solve the, find the Lumimotor geometry in 5D. Okay, it's not that easy even in 4D, 5D, but anyway, you can get this.
Sorry, Masaki, can I interrupt you again 1 second?
Yeah.
So as you said it before, but okay, just to make sure I understand, the original solution is probably not invariant under the fiber, right? The fiber that,
right.
Okay, you go from 5D to 4D. Right. So what are you doing? You're smearing along that fiber.
I am smearing along the fiber.
Okay, isn't this introducing some spurious singularity in the solution, or the solution after smearing still?
Logs.
It has logs. So the solution looks singular in 4D.
It is singular, and in this frame, it should be singular because you don't have a geometry. This is a D-brane solution. You have NS5 with D2 branes dissolved in it. Okay. So yeah. Okay. So all I can hope for is this non-closed time-like curve condition.
That's a question I guess I wanted to sort out. Mentally, I was thinking that what you've got is still a helical profile in 4 spatial dimensions, but because you're smearing on the Gibbons-Hawking fiber, it's turning the 1 over R singularity into a log singularity on a disk. Correct?
That's right. That's right.
But then you said something else. You said, I want to add some NS5 brane charge. Does that require that you have done that smearing or not?
No, NS5 should be there. NS5 should be there, and as you say, it should have this 1 over R singularity, but I'm smearing and getting the log.
Right. Okay. So the log isn't an essential part. It's just a convenient thing because you decided to represent it in 3 spatial dimensions.
Yeah. So things are just easier in this way.
Yeah.
Ideally, you want to do it in 60.
Sure, but okay, I take the point. But then there's going to be a follow-up question, which is going to be, you're going to see something interesting happening when that log branch cut slices across the green charge point. But if it's helical, can that green charge point be missed by the helix, or does the helix have to interact with the green charge point? That's coming later, I guess.
Okay, that is a good question.
Okay, let's wait for the.
Let's get there first. Okay, so the charges. So the default. Okay, what I'm talking about the default page charge, and that is nothing but the coefficient of the 1 over R terms in the harmonic functions. And that can be measured by this integral mathematically. And okay, if you want to measure this, then you have to consider this Gaussian surface at infinity. Then, okay, as long as you are away from any cut, you are free, you're safe, but you want to deform this into the ball. And this zigzag line is the cut for this gamma function. So we have this gamma, which is monodromic. So I have to take the cut to be somewhere, so I took it to be here. And then if you move the Gaussian surface like this, then there's some contribution from this blue part and the red part, because I just cannot deform this Gaussian surface any further. And I call this part, blue part, the localized charge, and this red part, the delocalized charge. because that's all I can do. So what happens? Okay, this is the point. So we start with a two-center solution with two codimension 3 sources. So this is the starting point, and we are displaying the D4 numbers. Here you have K units minus K units of D4 page charges. And now, as you move away from that south pole limit, then this codimension 3 D4 brane source expands into this codimension 2 source. And this codimension 2 source is on a latitude line of some certain spheroid, which is fixed if you fix D1 and D5 charges. And the D4 brane charge that was here now has split into localized and delocalized parts because of the multi-valuedness of the harmonic function. So you have this Gaussian surface that is on this disk cut, and from there you get this delocalized charge, and you also have localized charge. And as you change A and B, okay, as you proceed with the interpolation, this and this are not constant because A and B are changing, but the sum is a constant. The sum is just K. And at the point where this green dot intersects this disk, the charges jump. Because, how this happens is that because you have your Gaussian surface here, you have your Gaussian surface here, and to evaluate this thing, you have to evaluate gamma here. But the gamma has a branch cut, and its value jumps as you move across this cut. And that's why the charge jumps as you go through this cut. And in the end, what you find is that K plus K units of delocalized charge got transferred to the R equals to 0 center. And these localized and delocalized charges have changed. Oh, sorry, this delocalized one doesn't change. This delocalized one changes. And this is the same mechanism as Gregory Harvey Moore if you set K prime to 0, actually. And finally, your codimension 2-center solution becomes this 2-center solution with codimension 3 sources. Okay, I don't know if this clarified Nick's question in any way.
No, it just brings it to a sharper focus. When these are all, in a sense, in 4 spatial dimensions, these are all codimension 3. So there's a helix, there's a circle at the origin, which is the this K prime charge, and then there's a helix that's sort of interacting with that circle as you drag one through the other. And so I understand the branch cut story because you smeared it, but if you don't smear it, what does this jump look like?
So you're making this harmonic function to depend on the fiber direction as well now.
Yeah, I want to get away from the R3 and the fiber where you smeared. Just to say these are all sort of super tubey-like things in our Lumimotor geometry in R4 with a complicated helix undergoing monodromy through some other super tube-like thing. And so I just want to understand what this jump looks like from the point of view of the helical geometry.
Yeah, okay, this may or may not be relevant, but because we have gone to 2A, we have to take a TDLT along the psi direction. So in this NS5 picture, I just cannot have any structure along psi at the supergravity level.
Yeah, okay.
So maybe there's a duality transformation that keeps that structure, and maybe you can describe that structure in a harmonic function, maybe like in your paper with Ben.
But I guess also for Nick's question, for the intermediate configuration, you just have a helix. There's not like a helix plus a circle that you would transfer.
Right.
You start with a circle, you have a helix which deforms in various ways and finally ends up at a different circle.
Yes, that's it.
What's the point?
It's not that you have two separate objects where
Right.
charge
No,
gets
no.
transferred to another.
No, there's a single helix indeed. There's a single
It's a
helix.
single helix is just being observed from a different orientation. That's it. I was being stupid. Yeah. So what is this jump or interaction? Okay.
I think the jump is because, okay, if you think about the helix as a string, you have a Gibbon-Stocking charge. So if you think about the helix and, you're just, imagine some helix and, you are smearing it. It looks like a cylinder. But when you pass, so the cylinder, it's a cylinder in 3D, it's more like a string in 5D. So the best is to smear it in 5D and, think about the physics there, because, there you have the objects. And I think you have this Moore, this double car Moore phenomenon that, essentially you have a D6 charge and somehow there's a Gibbon-Stocking fiber that shrinks. And I think there's something about.
Is it something more naive? If I got a helix and I look at it from one angle, I just see some simple sort of supertubes. But if I turn it through 90 degrees, I see some other supertube. But then there's a natural flipping of the gauge choice for the B mu nu field that it's sourcing, or something like that, or the potential. And what we're seeing is a jump in the gauge choice.
It's related to the gauge choice, indeed.
So there's a large gauge. This is presumably some kind of large gauge transformation.
It is. It is. Yes. Yes. So in the 4D picture, in the multicenter solution, you have this gauge transformation, right, of the harmonic functions. And because your center has gone through this cut, you have, in some sense, gone to a different gauge. But because you want to be in a gauge that you impose. Because you want to fix the gauge at infinity. So if you have gone through the cut and one of your poles have gone to some other gauge, then you have to bring it back to the original gauge. That is somehow observable from infinity. That's consistent with the gauge at the infinity. Then you're going to change the default brane charge. So the no charges change, but it's only the way you see it changes.
Yeah, it sounds a little familiar from our Josephar stuff on, I vaguely remember threading charges through black rings and things like this. Okay.
No, so clearly for a black ring, for example, there are two patches, there are two gauges. One of them is with the Dirac string outside, and the other one is with the Dirac string inside. And, you have to go from one to the other one. When you move a super tube, for example, around the black ring and you collapse it, you have to be in the good patch, because, if you move a super tube through the inside of a black ring, for example, then if you're in a patch where the super tube and the black ring are not, where there's a Dirac string inside the black ring, then the super tube crosses the Dirac string, looks horrible. So you have to go to the good patch and then to move the super tube, and then you have to go back to the other patch.
And that's something you can do in 5D, but not in 4D, I guess. So in 4D, it looks like you have changed the charge, but in 5D or 6D, you have not.
I think it's similar in spirit to what we were doing with the supertube and going through the black ring. It has that feel about it where the local charges jump in this sort of Tachikawa sense of large gauge transformations. But okay, I have to think about it more.
Stefano, you have a question?
No, I was just suggesting maybe you should move forward in view of time.
Okay. Okay, so to summarize, so far, so we have found how to interpolate in the framework of multicenter solutions between this and this. And this coordination center played a crucial role in the setup. And this can be understood in terms of gauge transformation that in the sense that I just mentioned. Let me not go into this one. And some CFT viewpoint. So this is related to what Stefano mentioned. So the actual duo of the helical profile is not just that direct product that I wrote down, but it's the coherent superposition like this. And you have to change this coefficient A++ and A- to interpolate. And the sum is dominated by some values of N++ and N-, which are related to A and B. And this state is not an eigenstate of L JL or JR3, but it's a eigenstate of some particular combination of them. And this corresponds to the symmetry of the helical profile. So you have a helix with different pitches for 2 planes. And because of that, we have to adjust, you have to some particular combination of rotations so that this helix is invariant. Although this is not visible in our setup because we have smear. But even for more general interpolation that I mentioned at the very beginning, this structure must be crucial. So in more generally, what we want to consider is this and this spectral flow with general n interpolated between each other. And even in this case, we have to have this helical structure. So if we are to find any supergravity description of this, it has to have this helical structure. And one other comment is about the spectral flow. So CFT has this spectral flow symmetry. So I just talked about this interpolation. We can map this, we can flow this by spectral flow and go to this state with n. This corresponds to going from this interpolation to some other interpolation over here. And we can do this easily to the harmonic function because we know how to implement the bulk spectral flow. And we can certainly write down the harmonic function for this. And now this is a bit more interesting because now we are interpolating between 2 different 4D bases with different top knot charges at the 2 ends. So you have some structure of poles in V, and that structure is changing. And in this case, if you spectral flow, the coordination 2 sources are now, and it's not just NS5, but it also has this exotic 522 in this 2A frame. But if you go back to the D1, D5, everything is just Kazakhstan monopole because we are all just talking about the original Lumimotor geometry and the coordinate transformation. So you all you have is a Kazakhstan monopole. And what's interesting is that this also works for the fractional spectral flow of GLMT. So, GLMT or you guys, some of the people in the audience thought about flowing some point here, well, not exactly here, maybe some other point here, into some point in the bulk here by some fractional spectral flow when some quantization condition is met. We can do the same thing for this flow, this interpolation, and you can consider some interpolation that sits in the middle as long as some quantization condition is met. Namely, the endpoints must satisfy the quantization condition, but still, if that's possible, then you can interpolate between 2 different GLMT solutions.
You have about
okay,
10 minutes, Masaki.
Okay, 10 minutes. Okay, so here are harmonic functions. And okay, one last comment. One amusing thing is that if you consider K and K prime to be 1, then what you are doing is to start from here and going here and then here and here. So you can go up this polygon like this. And what you're doing is to start from some 2-center solution and moving one center around the other like this to go to this configuration here. And then now you interchange the role of these 2 guys and do the same thing. So you're going from this to the other one like this, and you keep doing this like this. Then this corresponds to going up this hill. So that's a bit interesting. Okay, that's the last thing I wanted to say in the main part. So after all this discussion, what is the dual of a more general interpolation? Not clear at this point to me, but all I can say is that the helical structure must be relevant. And also, it's going to probably include the helical structure, which can be visible as a codimension 2 solution, codimension 2 centered in this multi-center solution setup. And for constructing such solutions, this technique that we just developed here must be useful. And it's interesting to study is the most general solutions involving codimension 2, and that in that direction I tried a bit. And one other thing is that, okay, so PL and Mondal constructed some multicenter solution that corresponds to the microstates, the pure Higgs branch states, perhaps, of some D6, D2, D2, D2 configuration. But they did not include codimension 2 centers. So maybe if you include codimension 2 centers, maybe there are going to be more solutions, and maybe you can find Higgs branch states for not just for one D6 frame, but for 2 D6, 3 D6. I don't know. That's just worth trying, but I don't know if that's going to work. It's interesting. Okay, that's all. Thanks.
Okay, thanks a lot. Then we should thank Masaki for a nice talk. Thank you.
And,
And of course, we have time for questions. We already interrupted you several times, but of course, please ask questions.
Yes, please.
I guess oh, sorry, go ahead, Stefano.
No, please.
I was just going to ask, there's this sort of story that we talked about a year or so ago about having to do with magnons, Masaki, and
yeah.
I just trying to join up the dots between what you're doing and the magnon story. So the magnon is the idea is that you have a fundamental string, say you've got a super tube, or a superstratum, you can stretch a fundamental string across diametrically across the super tube.
Right.
But then to make it BPS, you have to add NS5 brane charge and so forth. And then you can, if you put enough open strings of diametry across the super tube, then it should be coherent and should be a geometry. And so that was the sort of thinking we're having there. This looks qualitatively rather different. So can you join up the dots between the magnon story and what you're doing here?
That is a very good question. So did we conclude that if we add NS5, then this is going to be supersymmetric?
Yeah, but that's just the usual. This is the thing that Joseph preaches on about quite often. He's still here, but which is the usual story. If you have the D1, D5 supersymmetries, the question is what's compatible with that. If you put in an F1, it cuts the supersymmetry in half because it's another projector that's compatible. But if you just put pure F1 charge, one magnon cuts the supersymmetry in half. Once you put two magnons, you're screwed because you have two different projectors geometrically or related to one another. But you destroy all the supersymmetry. However, if you take the NS1, fundamental string charge, NS1 if you like, charge, and couple it with NS5 brane charge and the right density, then precisely you get the supersymmetry projector which is compatible with the D1, D5 system, and you can put them anywhere. So the right combination of NS5 and D1 and F1 charges is compatible with D1, D5 system. This is what Z4 does in our favorite story. It is actually turning on F1 charge and NS5 brane charge in a self-dual manner so that the supersymmetry is compatible.
Okay,
So
maybe that thing is solved. But what confuses me is that we don't have that helical structure because this magnon is only along this equator direction. But you have to have some other direction to have a helical structure. So in some sense, this is only along phi and maybe theta. So this magnon is only along phi, but you want to have something else.
It's entirely in an R2 in some sense, and so therefore the other R2 is untouched. So your U1 that you've got is some tilted combination of the two U1s, hence the helix, whereas the magnon I was thinking of was living entirely in an R2 and it was just stretching across the supertube disk.
Indeed.
So it's a different U1, and it's probably a different set of states.
Yeah, and why that is so they say that this magnon corresponds to J minus something plus or whatever. But this plus is only one unit, but you have this big number as this level number, and this level number is becoming the length or the arc angle in this plane, right? So, okay, so even for 8 is 5, you insert W inside Z, right? And this W has some R charge, but you always talk about this plane disk inside disk S5. You never move out of this disk because this W has really small charge compared to the momentum index that you have. So it's not actual momentum. This momentum index that corresponds, momentum number that corresponds to the angle in this on this plane. So I think if you want to have some helical structure visible, they have to also have some big R charge. So you don't just have J plus, but you have to increase this plus by, I don't know, taking a power of this J.
Okay. I'm not following entirely, but okay. We should probably talk about it later.
Yeah.
Okay, Stefano, probably you can ask.
Yes, thanks. No, yeah, I was just confused. Sorry, what's the relation with this Gregory-Harvey-Moore process, and why you said you can transmit the solution within supergravity, but why? If it is why you can just glue in some of Fourier mode close to the source that transmit the solution, or is it
Fourier mode?
Sorry, I don't know what's the relation with what you described and this Gregory-Harvey-Moore. What I have in mind is, if I remember it, there is a tabula space in that case, and then you can unwind a string, one string around the KK monopole because of the op vibration. And then there is a compact version of that, which is in codimension 2. If you compactify one direction, then you just get a pinch torus. And then that process is essentially a then twist of the torus, which is the monodromy of the A-type singularity. And then you can go from one to the other by gluing this Uri-Vafa correction that brings one to the other. So I don't know if I have in mind something completely different or...
okay, I don't know about that torus thing, but in this Gregory Moore Harvey paper, they say that you don't have to go to the center to unwind the string. You can be at some constant radius and play with the shape, and then you can unwind this, right? And that's exactly
but that's in codimension 3. I don't understand what's the relation with the log profile, which is more codimension 2.
Okay, but it's not really about code dimension. So this process of going from this to this is exactly what they have in their paper. They consider some particular shape of the fundamental string sitting at a constant distance, at a finite distance from the center, and they somehow change the shape staying at a constant distance and then unwind the string, right? And this is exactly the thing I have here when k is 1 and k prime is 0. So I said that as you move, some charge is transferred from the fundamental string, well, this D4 brane to the center, and when k is 1, k prime is 0, then exactly 1 unit of fundamental string charge is transferred to the center, and in the end, you have 0 fundamental string charge. So okay,
yes, but you're not then smearing this configuration somehow. No, it's
okay. Just interpret this picture as the projection of the fundamental string profile. Just ignore the fiber direction and just project. And then this is exactly what that fundamental string is doing. I'm confused about smearing and the charge, but this should work the same way.
Yeah, I have to think about thanks.
Yeah, I have to think about it too.
Okay,
I have a couple of questions. One is very short. So nice talk, by the way, very nice talk, Masaki. So first question is just a little curiosity. There seemed to be a special case of parameters where the localized charge can, in principle, go to 0 when a squared k equals b squared k prime. And I wonder if is there anything that forbids that to happen in practice, or is it possible?
Localized charge is 0.
If you go plus or minus a slide, I think we can see the expression.
Sorry, no, not this one. I didn't write down the. How do I do this?
Yeah, that's all it. Yeah. So I'm just thinking about the numerator of this Q localized here.
Yeah.
Is that a special case that something interesting happens, or is it just?
Okay, I'm not sure.
It was also a factor that was appearing in some of your harmonic functions when you added the extra terms to make everything harmonic. Some of the terms were proportional to this numerator. So it just looked like there might be a simplification there, perhaps.
Yeah, okay, it does simplify, but I don't know the significance of that. Okay, that's interesting.
Okay, I mean, that's just a curiosity. So then the other main question was, can you comment a little bit about making a bit more about the generalization of this to really a GLMT type interpolation between two different types of GLMT strands?
I said that this is not so clear, but my feeling is that this, okay, so my first naive guess was that, okay, because I have constructed a solution in which, okay, so the thing is that if you are only playing with coordination 3 center, then we know what to do. We only want to have half BPS primitive centers. But I wanted to have an analog of a primitive center for coordination 2 brain, coordination 2 center. And I have that now in some sense, because I have just puffed up the thing. And however, this doesn't seem to be enough, because by puffing the thing up, I'm not really doing much, because D4 becoming NS5 is in some sense tilting the direction. So if you go back to the D1, D5 frame, you're only changing the direction of the NS5. So NS5 can be along the fiber direction or the base direction, and that's just tilting of KKM. And it's not really a fundamental difference. So changing D4 into NS5 in the type 2A frame is a very simple thing. And this doesn't seem to give me enough degrees of freedom to go away to lift from this bottom line of this parabola. I need some more ingredient. Maybe I have to consider not just this single center puffing up into a coordination 2 brain, but maybe this is going to puff up into coordination 2 brain and also some other coordination 3 brain or something. So this is like going back to what we discussed in Kyoto several years ago.
Right. Mm-hmm.
Yeah. Well, I'm trying to think a bit more if I can.
Sorry, connecting to the same question that David just asked. So in the general case, in the interpolation between, let's say, GLMT, as you want to call it, solutions, as you also said, you're not guaranteed that the interpolating solution is supergravity solution, right? Contrary to the case in the case you have considered, the whole interpolating solution is certainly a supergravity state. But in the general case, as you also said, it's likely that the interpolating solution is actually a string state. So what do you think is the appropriate framework to study this type of solutions? Are you still solving supergravity equations or what?
Okay, so I think more pedestrian way, I guess, is to, if you want to go step by step, as Nick was saying, we have to consider what this magnon does. So this flowed state is a magnon in some sense. So it's a fundamental string, and we want to know what is the shape of that thing. And we are going to excite this thing a lot. So that is going to puff up into this fundamental string is going to be a D-brane. And maybe if you excite this more, this is going to become a geometry. And I didn't want to do it. And I thought that this way I can shortcut that and get to the solution. But this may not work. So we have to carefully look at what kind of magnon you get and what kind of D-brane that puffs up into.
I guess you might want to make your little L parameter on the slide something like an epsilon times capital N. If you want to skip over some of those stringy or brane things and go straight to a back-reacted geometry.
What did you say?
So I mean, the back reaction, the sort of, to get from a heavy string through a D-brane to a back-reacted geometry, the back-reacted geometry should be when little L here is of order capital N. But it can still be epsilon times capital N, where epsilon is a small parameter.
Yeah.
And so that might be a way to sort of bypass the regimes of more stringy things, at least formally. So you can still control epsilon from 0 to 1, but where in terms of the capital N scaling, it's always going to be something which scales with capital N in the large N limit. So it's likely to be something which is back reacted and giving you a new geometry.
So you said that you control the number of excitations like this.
Yeah, that's your little L, if you know what I mean. And epsilon goes from 0 to 1. And then, of course, when it's very close to 0, you get back into the stringy and brane thing. But if you keep it like this, then at least formally you're in the regime where you have the best chance of at least having a back-reacted solution.
Okay, so do you want to say something more, Masaki, regarding David's point?
Not about this particular point now.
Okay, we have more questions. Okay, good. Then if we don't have more questions, I think we should thank Masaki again. Thank you.
Thank you very much.